Today on Macaulay Math, combinations, compositions, and inverse functions. Intro. Okay, good day. I am Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 3 on combinations, compositions, and inverse functions. Our goals for today: we're going to find the domain and range of functions. We're going to find simple combinations of functions. We are going to compose functions. We are going to find the inverse of a function. And then finally, we are going to determine when a function's domain must be limited to find an inverse. Today, we are talking about how we put multiple functions together. Adding, subtracting, multiplying, and dividing functions are common operations. In addition, we will be talking about the concept of composition, where we plug one function into another. Finally, if a function takes an input value, manipulates it, and creates an output value, then the inverse of that function takes the output value and manipulates it to give you back the original input value. Let's get started. Okay, let's start with a couple of definitions. First, a function f from a set A to a set B is a relation that assigns each element x in the set A exactly one element y in the set B. The set A is the domain, or what we call the set of inputs, and the set B contains the range, or the set of output. The set B can actually be bigger than the range. Finding the domain. When we are asked to find the domain, we're always going to start with all real numbers. In many functions, the domain is all real numbers. But after we have looked at all real numbers, we then look at the function, and any input that causes a division by 0 must be removed. Any input that causes the even root of a negative number must be removed. Later we will expand that to any input value that causes a negative inside of a logarithm must also be removed. And finally, this third one is not algebraic, but it does go along with some of our application type problems. Any input that does not make sense in the context of the problem must be removed. As for instance, you cannot have a negative TV. So if one of your axis, either the X or Y axis, is measuring number of TVs, you can't really have a negative TV, so that might have to be removed. To find the range, once the domain has been determined, input all of the domain values into the function, and the set of resulting values is our range. Simple combinations of functions: if you have two functions, f and g, and you want to add them, you just add the two functions, and that will be basically combining like terms. If you are subtracting two functions, you must distribute the negative to the second function and then combine like terms. The product of two functions, f times g, will be the product of the two functions, and many times if they're polynomial functions, all they'll have to do is distribute. The quotient of two functions is just f over g, and you have to throw out any values for x that causes g of x to be equal to 0. And so you have to throw those out, because then you'll have a division by 0. We can't have that in our functions. Some elementary examples. Let's suppose that f of x is 3x squared and g of x is 2x minus 3. Then if I'm asked to evaluate f minus g of x, we are going to see that that is going to be f of x minus g of x, and once I get there, all I'm going to do is I'm going to substitute the expression of both of those two functions in, and that'll give me 3x squared minus, and since I'm subtracting, I have to subtract the whole quantity, so I'll put parentheses around that for now. And then to simplify that, I'm going to distribute the negative to both terms, which will give me 3x squared, and then minus 2x, and then plus 3. But none of these terms are like terms, so they cannot be combined, and that is going to be my answer for that one. And again, these are elementary examples. F times g of x is going to be f of x times g of x, which will be 3x squared times 2x minus 3. And there we will just distribute. So 3x squared times 2x is going to be 6x to the third. And 3x squared times negative 3 will be negative 9x squared. Put a box around that, and we are finished. Next, composition of functions. The composition of function f with the function g is f composed with g of x. Now, this raised circle is a operation unto itself. It's an operation just like this symbol implies multiplication, this symbol implies division, this symbol implies addition, and that symbol implies subtraction. This symbol is going to imply composition. And what we are essentially doing when we compose functions is we are plugging one function into another. The domain of f composed with g is the set of all x in the domain of g such that g of x is in the domain of f. And so basically you start with the domain of g, and any value that is in the range of g that is not in the domain of f also must be removed. Some elementary examples. If I say f of x is 2x squared plus 1 and g of x is 3x minus 1, and we want to find the composition of f composed with g of x and g composed with f of x, the reason I'm doing both of those is to illustrate that while multiplication and addition are commutative, meaning that you can add or multiply in any order, 2 times 3 is equal to 3 times 2. That is not true with composition of functions. So if I am asked to compose this, this is f with the g function plugged in. Now the g function is defined here as 3x minus 1. So we're going to plug that in for g, and I'll have 3x minus 1. And then f of x is defined as 2 times something squared plus 1. 2 times something squared plus 1. In this case, that something is 3x minus 1. Now, when I square this thing, I have to FOIL. Remember, you have to multiply, and I'm going to do that on a separate page. So we'll add that in. 3x minus 1 squared is 3x minus 1 times 3x minus 1. And so here I have to distribute. 3x times 3x is 9x squared. 3x times negative 1 is negative 3x. Negative 1 times 3 is another negative 3x. Negative 1 times negative 1 is positive 1. I collect my like terms. I've got 9x squared minus 6x plus 1. Come back to the original, and I will have 2 times 9x squared minus 6x plus 1, and then the plus 1 from here. I'll distribute the 2. 2 times 9x squared is 18x squared. 2 times negative 6x is negative 12x. And then 2 times 1 is 2. And then we'll just skip a step and add that 1 and say it's plus 3. The next one, g composed with f of x, will be take the g function and plug the f function into it. And so the f function is 2x squared plus 1. And then the g function says 3 times whatever's inside those parentheses minus 1. So 3 times whatever inside the parentheses minus 1. In this case, that something is 2x squared plus 1. And so in this case, I don't have to square anything, so I just distribute. 3 times 2 is 6x squared. 3 times 1 is 3. And then minus that 1 will give me plus 2 as my final answer for that one right there. Inverse function. An inverse function is a function formed by interchanging the ordered pairs of a given function. The domain of the original function becomes the range of the inverse function. If the original function is denoted by f, then the inverse function is denoted by f raised to a superscript of a negative 1. It's kind of hard to see here. f inverse of x. That's how I'm going to read that. That's not to the -1 power. This is just the notation for inverse. To show that two functions f and g are inverses, compose f with g, then compose g with f. Both of those compositions should reduce down to x, and I'll show an example of that here in a moment. An elementary example, show that the following functions are inverses of each other. We have f of x is 3x minus 2, and g of x is x plus 2 divided by 3. To show that they are inverses, we have to compose f and g with f, and they both must reduce down to x. So let's do that. F composed with g of x is f of g of x, and I will substitute g into f. So f of g is x plus 2 over 3, x plus 2 over 3, and then we'll plug this into the f function, and the f function is 3 times something minus 2. That something in this case is the x plus 2 all over 3. These 3's will cancel. X plus 2 minus 2. These cancel, and I'm left with just x. Then I have to compose g with f of x, which is g of f of x. And f of x is 3x minus 2. G says take something, add 2 to it, and then divide the whole thing by 3. That something is 3x minus 2. And I want to add 2 to it and then divide by 3. In this case, those parentheses can be dropped because I don't have any distributing. I don't have any exponents. So I've got 3x minus 2 plus 2. I end up with 3x because these two will cancel. 3x over 3 reduces down to just x. And since they have both reduced, both f composed with g of x and g composed with f of x have both reduced down to x. Thus, we can say f and g are inverses. Okay. For a function to have an inverse, it must be 1 to 1. And as a definition, a function f is 1 to 1 if for every a and b in its domain, f of a equal to f of b implies that a is equal to b. Now, what that means graphically, let's look at Desmos real quick. Here, I start with y is equal to just x, and that's that red line that I have right there. For a relation to be a function, it must pass a vertical line test. And so I have this vertical purple line, and if I move it back and forth, that vertical purple line never crosses the red line more than one time. So since it passes this vertical line test, we know that y equals x, the red line, is a function. If we want to say that the red line is a 1-to-1 function, it must also pass a horizontal line test. Now I have a green horizontal line, and here if I move it up and down, that green horizontal line only intersects the red line at one point at any one time. Since the red line passes both a vertical and a horizontal line test, it is 1 to 1. So the line y is equal to x is a 1 to 1 function. The blue curve is the simple parabola y equals x squared. Now if I go back, again, y equals x squared passes a vertical line test, so it is a function. It does not, however, pass a horizontal line test, and therefore it is not 1 to 1 in its current state. Additionally, one last one for quick reference, This is a circle. I know it doesn't look like a circle, but you can see that it goes through 0, 4, 4, 4, 0, -4, and -4, 0. And so the scale is a little wider than it is tall. It is a circle. It does not pass a horizontal line test, and it does not pass a vertical line test. So the relation x squared plus y squared equals 16 is neither a function nor is it one-to-one. To find an inverse, you're going to essentially switch the x and y values of the function and solve for y, provided that the function is one-to-one. Now we can limit the domain so that a function is one-to-one. In Desmos, the way that we do that, remember this was our non-one-to-one function, I can limit the domain. I can come up here and I can put this expression with the brackets, x is greater than 0. And so this says now we are talking the function y is equal to x squared with the domain limitation x is greater than 0. And so right now it passes both the horizontal line test and the vertical line test. So this particular function with the domain limitation is one-to-one. Limit the domain to find the inverse of a given function. F of x is equal to x squared minus 2. If I go to Desmos and I clear all of this stuff out and I go, we can see that this thing right here is one-to-one with the same domain limitation that I had in the last one. So what I'm going to do is say that we are limiting this domain, and the way we're going to do that algebraically is we're going to put a semicolon. It is the function f of x equals x squared minus 2 provided that x is going to be greater than or equal to 0. And then what we will do is we will rewrite this by switching our x and y, just like we said in the last slide. So I have x is equal to y squared minus 2. And then I will solve for y. So the first thing I'll do is I will add 2 to both sides. That'll give me x plus 2 is equal to y squared. And then I will take the square root of both sides. And that will give me y is equal to plus or minus the square root of x plus 2. Now, whenever you take the square root, remember from Algebra 2, you have to consider both a plus and minus. But in this particular case, since we've limited the domain, we only have to consider the positive. And so my final is f inverse of x is equal to the square root of x plus 2. And we can go to Desmos and go f of x is equal to and we get a new function, and any function and its inverse are reflections about the line y equals x. So if I type in y equals x, you can see that 0, -2 becomes -2, 0. We can see that the point 2, 2 is on both curves, because if I switch 2 and 2, I get that value. So I feel fairly confident that these are inverses. Well, that's all I have for today, folks. So the Star Wars fun fact of the day: in Empire Strikes Back and Return of the Jedi, Yoda has 4 toes, but in The Phantom Menace, he has 3 toes. So a continuity error there. That's all I have for today, folks. Have a good day. Goodbye.